All right, now recording. All right, yes, good afternoon, everyone. Thanks for coming along. Well, good morning, good afternoon, depending on where you are. I think we've got people all over from New Zealand to WA and everywhere in between. So the Vic Tas chapter of PIANC ANZ is proud to introduce Professor Alessandro Toffoli and Dr. Filippo Nelli. They're both from the University of Melbourne. Alessandro is going to provide a brief introduction for us just on his group and what they do, and then Filippo is going to give us a presentation today about ship hydrodynamics and Antarctic exploration, which I hope should be very interesting for all of us. Just beforehand, a quick little bit of housekeeping. If everyone's happy just to turn cameras off and put yourselves on mute during the presentation, that would be nice. And if you've got any questions, just pop them in the chat, and at the end of the presentation we can address them. Just a quick 2 slides on a bit of background on PIANC. I assume most people here are very familiar with PIANC, this being a PIANC event. I won't go through all of this, but just a reminder that to get involved with your local chapter, there's always gatherings and events and webinars and things happening. At a minimum, make sure you're on the emailing list, tell your colleagues. If you don't know who your local PIANC chapter representatives are, we have them in every state and territory and in New Zealand, then maybe just jump on the PIANC Australia website, PIANC Australia New Zealand website. I'll just post a quick link in the chat and you can find plenty of information there. And last little bit of information, just a reminder about APAC 2020, which is our Asia Pacific conference happening in Fremantle, end of November, start of December. For those of us lucky enough to be able to travel to Fremantle, this is a hybrid event, so an in-person conference for those who can get there. For everyone else who can't, everything will be online, so sign up and still attend all the presentations and various networking events. Should be good. I think there's already quite a substantial group have signed up to be there in person, so that's good. Early bird registration is still open for a few weeks, so get along to that. I'll also post the link in the chat. 2020.com. All right, Alessandro, I'm going to try and present your slides if you want to talk to them.
Yeah. So if you launch my my slide, that would be good.
Yeah.
Anyway, hi everyone. I would like to thank Lawrence and Chris for giving us the opportunity to show some of the work that we are doing at the University of Melbourne. Despite our accents, I really hope you will find our slide and work interesting. If you have any further question or point of discussion, we'll be very happy to take the conversation further. Just a very brief introduction to my group. I basically, the group is rather small. I have a research fellow, Filippo Nelli, who will give the presentation very soon. Plus, I have another research fellow share with the University of Adelaide, who contribute quite a lot to the slide that we're going to show. Plus, I have a number of PhD students, but I'm in a period of renewal of students because most of them are either finished or waiting to graduate. So we need to have new people, new fresh people coming on board. If Lawrence, you can go to the next slide, that would be great. Just a very brief overview of what we do. We are very much biased towards the wave field, so we are interested in anything related with ocean waves, both in the deep ocean, far offshore, and closer to the coast, including coastal morphology. We have been tackled our research with different means. Historically, I've done a lot of work experimentally, accessing large facilities in Europe. In the facilities that we have available at the University of Melbourne, including a 60-meter-long windwave flume.
Oh, the one that, yeah.
We have done quite a lot of numerics, developing, using forecasting model such as Overwash 3 model used by the Bureau of Meteorology. But we also have advanced model for phase resolving and getting individual wave height and stochastic properties. Plus, we have been involved with Filippo in computational fluid dynamics very recently. Because we, at least speaking for myself, I had a target in life to see Antarctica at least once. So I get involved with a colleague of mine in the, field observation in the Southern Ocean and closer to the continent, the Antarctic continent at high latitudes. And we have been involved with a colleague in South Africa and colleague here in Australia to develop a system of stereo cameras to detect sea ice properties and ocean waves by reconstructing the 3D surface. Yeah, that's all I have to say, and I will leave the floor to Filippo, who will give some details, more details on the research that we have been doing.
Thank you, Alessandro. And Lois, if you can. Okay, perfect. I'm gonna share my presentation. Okay. So, hello everyone. My name is Filippo Nelli, and Alessandro, as Alessandro just said, I'm a research fellow at the University of Melbourne. I've been working with him since I've started my PhD here in Australia in 2015. So now it's been more than 5 years that I've been working with him and his team for working on mainly on Antarctic research. Some of you in the OMC environment already seen me, and especially in the last 2 years, I've been in and out of OMC, working especially with Reza and Greg Ebert, basically on the couple hydrodynamics and ship model, basically to compare it with the OMC already in-house developed one. And today I'm going to give a detailed presentation of what we are doing on Antarctic research and how this is linked to the ship hydrodynamics principles. So basically this is the work I've been doing with Professor Toffoli and in collaboration with Marzia Dercani, our PhD student that I've seen. She's actually here in the meeting watching this presentation. And Dr. Alberto Alberello, who's basically our Cristiano Ronaldo of the research fellow, which is because he's collaborating with us with the University of Adelaide and now with the University of Turin back in Italy, and has done a large chunk of this research activity. So let's start with a bit of introduction of the role of sea ice on climate. So basically, sea ice, especially in the last 10 years, has been made room into the news for the climate change, the reduction of sea ice, mainly in the Arctic Ocean, and basically the decline of sea ice in the Arctic Ocean in the last 30 years has been quite significant. And this basically has a lot of effects on a global scale because it affects the heat transfer between the ocean and the atmosphere, because as you can see here in the schematic drawing, the ice is has an effect known as albedo effect. So it reflects the solar radiation from the water, so it prevents the water to heat up too much, and the reduction of sea ice produces an effect called the Arctic amplification. So more solar radiation is entering into the water. This warms up the water, shrink the ice even more, which opens up new areas, so more heat, and basically it's a vicious cycle that's reducing at an alarming level the sea ice in the Arctic Ocean. This affects also the ocean mixing, so the temperature of the water in the polar region. So we have the presence of ice and the basically the mixing of the water in this region is completely different of the water in the ice-free region. And of course, this creates submarine currents going between the polar region and the temperate region without ice, and there is this submarine circulation of water that's undergoing, and it's due to the presence of the sea ice region in the Arctic. On a regional scale, the presence of sea ice has a direct effects, of course, on ice shelf. So depending by the seasonality, so if it's summer or winter, we have that so-called marginal ice zone and ice shelves that can extend or shrink into the Arctic and Antarctic Ocean, depending, of course, by the temperature and the solar radiation. This consequently affects the coastline of the polar region. Just think about the bay in Canada, the Northwest Passage. It's open or closed and accessible depending by the season and the presence of ice. And last but not least, the presence of ice, it's a main parameter for the habitat and for the animals living in the Arctic and Antarctic area. Just think about the struggle of, for example, for polar bears due to the reduction of sea ice in the polar region. Basically, it's shrinking ice. It means less habitat, less food for them, and it's posing a threat to their actual existence in the polar region. So, as you can see, the sea ice, it's very important, not just because it's a bunch of ice in the North Pole and South Pole, but because it has a direct influence on the planet at a global scale. So, how do waves affect ice? As Alessandro said in his introduction, we decided to focus on the waves and this aspect of wave and ice interaction. So, what's the mutual interaction between ocean waves and sea ice? So we can say basically that the waves affect ice and ice affect waves at the same time. So what's the action of waves on ice? First of all, waves break up the ice. That's pretty can be intuitively, if you can see in this video. I don't know if it's working. Anyway, you have the wave crashing against your sea ice, and basically this, as you can see in this schematic, is cracking the ice when this reaches the breaking point, and it creates a large, from a continuous cover, it creates a fractured cover. Once the cover has been fractured in a series of ice flows, as you can see here in the drawing, the flows can be moved by the wind wave action. Combined can create earth flows into the ocean and areas where basically there is no ice cover. And once flows can be created, group of flows are created into the ocean, and flows are close to each other, they collide, they bump into each other, and they crash. So basically from large flows we obtain flows smaller and smaller until we reach warmer water and they completely melt. So as you can, it's possible to see that basically waves affects ice flow concentration and flow drift and distribution, and of course has a direct influence of the albedo effect and reflection of solar radiation. At the same time, the waves are affected by the presence of ice, and the main action of ice the main action of ice on waves, it's the attenuation. As you can see here in this graph, you can see the wave spectra from 0 kilometers, so basically when we are in open water and there is no ice. And as far as we progress into the ice-covered region, the spectra is attenuated, and it's basically the spectral amplitude decrease until when basically we are 500 kilometers into the ice-covered region and the waves are almost entirely attenuated. So there is this mutual interaction between sea and waves. Sorry, the video is not playing, I don't know why. But we are struggling with the videos. I don't know why they were playing this morning, but not now. Anyway, with a single flow interaction. So let's go back from the bigger picture sea ice. We decide to investigate the wave and point of view on the interaction with sea ice. Then instead of focusing on the large cover, we wanted to evaluate the interaction between waves and the single ice flow. So basically, instead of considering hundreds of kilometers of sea ice cover, we wanted to have a look at what's happening in a single ice flow or 10 or up to maximum 100 meters. So how did we decide to tackle this problem? So we engineered this pioneeristic experiment, since we were the first one to try this kind of approach. So basically in the 60-meter flume at the University of Melbourne, where we have a wave maker and a beach, we use this plastic panel. Basically, we put it into the water, mooring it front and back, and we evaluated the interaction between monochromatic waves of different period and amplitude with this plastic panel, which was basically a model for the ice flow, and we evaluated what was the reflection and transmission of the waves generated by the plastic panel. And what we have seen that basically for small amplitudes, the actual existing linear model were able to correctly predict the reflection and transmission of the wave operated by the panel. But the more we were increasing the amplitude of the incident wave, the steeper the waves were becoming. Basically, the more there was a divergence between the linear model and the actual observation. So we observed that something was not actually predicted by the linear model. So there was some kind of non-linearities triggered into the wave-ice interaction that we didn't know exactly what was going on. So we noticed also that basically the overwash, so basically the green water on top of the plate, was increasing with, of course, the increase of the incident wave amplitude. So we decided that we wanted to investigate more this phenomenon. Basically, at the same time, we compared the flexible movement of the ice with the linear model, and differently from the wave behavior, which showed no linearity, the flexible movement of the plate was actually in line with the linear model of the team, based on team plate theory. So we placed this motion sensor on the surface of the plate, and we produced the movement of the plate, and we compare it with the movement predicted by the theory, and we noticed that for the first, basically for almost every modes, there was a good matching between the linear theory and the experimental movement of the plate. So while waves were showing some kind of non-linearity, the motion of the plate was actually correctly predicted by the linear model, even in presence of water overwash on top of the plate. So basically, this was what we were able to get out of the experimental test. So to evaluate the nonlinearities, we decided to run some computational fluid dynamics (CFD) test to have a look basically at the velocity field and in the water near before and after the plate. So what we've done using OpenFOAM, we created basically a copy of the experimental setup, so a monodimensional wave flume, and where basically we created the same waves as in the experiments, and we evaluated the interaction of these waves with a rigid body, which was basically of the same size of the plastic plate we tried in our experiments. And first of all, we calibrated the model, tried to reproduce the same reflected and transmitted wave amplitude, just to see if the CFD was able to capture the nonlinearities we observed in the experiments. And we obtained a very good agreement between the experimental results, the yellow dots, and the triangles, the CFD results, both for the 0.8, 0.9, and 1 second period. So once we validated the model, we've seen that basically the results were matching. We wanted to have a look of the velocity field. So we reconstructed this, which is basically the turbulent field under the plate, and we noticed that we had a lot of turbulence going on into the overwash as predicted, but also we had a big amount of turbulence going on just after the plate, when we had the flow back of the water from the overwash region back to the wave field under the plate. So we were not expecting to see all this turbulence be after the plate, and basically we find out that's where the most of the energy dissipation takes place. If you take a look at this graph, this is the amount of energy dissipated at 0, which is the front edge, and 1, it's the rear edge. And we have this spike, which is basically the rear edge of the plate. So the flow back of the water from the overwash back to the wave field creates this spike of energy dissipation, the dissipation rate, which basically fades as long as we progress towards the end of the flow. Then we have this diffuse dissipation below the plate due basically to the slamming of the plate up and down, and this additional spike, of course, here at the top, because in the front edge, because we have also a bit of flow back of the water also at this part of the plate. And again, also with the CFD, we were able to see that we have this increase of nonlinearities with the increase of the incident amplitude of the wave, but accounting the energy linked somehow to the overwash, both on top of the plate and basically in the surroundings, we were able to reconstruct almost entirely the amount of energy included in the incident wave. So thanks to the CFD, we were able to find out how the energy was dissipated, where this energy was going, and we had a clear picture of the wave-ice interaction between a single ice flow and an incident wave field. Not only the CFD was used to calculate the energy dissipation, but thanks to the CFD, we were able to see also the effects of the overwash on the response amplitude operator of the plate. Of course, since we had all these nonlinearities going on in our model, we couldn't use any linear model like the NEMO, for example, where we had to calculate it through the CFD. So what we have done, we created the standard experiments, as you can see here, with overwash, and the same plate, but with a thicker edge to prevent any overwash water on top of the plate, but with the same mechanical properties of the thin plate. And what we noticed that while the pitch more or less was unaffected by the presence of overwash, except a bit for the highest incident amplitude, the eve movement of the plate, thanks to the presence of water on top of the plate, was strongly affected already for mid, not only for the steepest wave, but also for mid amplitude. So we were able to reconstruct the effects of the overwash that it can have on the floating body and the hydrodynamics of the flow in both with and without overwash. So this was basically the research using the numerical model with a single body. So the next step was to step up. So what's going on when we have more than one ice flow? So that's what happens in nature. So as I was saying at the beginning, the waves, thanks to increase the concentration and herd flows all around to each other, we have collision. So using CFD, we created a model with two independent floating bodies, which unfortunately is not working. And as you can see here in the results, these blue triangles are the results with one plate, and adding a second plate here strongly increased the nonlinearities, mainly in a space between the two plates where we have the interaction between the transmission from the first plate and the reflection from the second plate, which creates additional turbulence and additional energy dissipation that, of course, increase with the increase of the incident amplitude. And also, we evaluated the response up to 10 floating bodies. Of course, we didn't have the computational power to calculate 10 floating bodies with the CFD, so we just did it using the linear theory and NEMO. And we noticed, but this was good enough to notice that even with the linear theory, so without accounting for nonlinearities, we noticed that, for example, pitch, heave were affected in the last body, as you can see here in the graph, and also much more than the first body. So even just sticking to the linear theory, we notice a mutual interaction between the floating bodies when they are close to each other. This was basically our work in the lab and using numerical model. Then how did we link this work to the real ocean? So now we can have a look at what was going on basically on the Southern Ocean during the Antarctic cruise. We had the chance to participate. And the first problem that we had to face when we moved to work with the Southern Ocean is that we don't have any observations. So for this large chunk of Southern Ocean, we had to rely just on 3 buoys far away from each other. So we didn't have any reliable observation to account to have basically wave data to work on it, and especially in the close to Antarctica in the ice covered region. So we didn't have any data to analyze. So the first attempt to try to solve this issue was to use the VAMOS system. So in the first Antarctic expedition, we had the chance to participate. So it was the Antarctic Circumnavigation Expedition, EACE, between December 2016 and March 2017. And basically, this was the 3 legs of the Antarctic cruise, starting from Cape Town to Hobart, Hobart to Punta Arenas back to Cape Town. And on the academic Tereshnikov, which is basically the ship that was used to do this Antarctic cruise, was set up the VAMOS, which is basically a radar. And basically the VAMOS is a radar that creates a picture of the wave field in the surrounding of the ship, and creates a 2-dimensional spectrum based on the reflection, the scatter reflection that the radar is receiving from the sea surface. Oh, this is working, thank God. And this is an image of the VAMOS, and now it works. So this is like the radar observation surrounding the ship. So we can have a 2-dimensional sea surface reconstruction, and from this one we can obtain a 2-dimensional spectrum in the portion of the ocean where the ship is traveling. Problem of the VAMOS that it doesn't work in sea ice covered, because the presence of ice strongly affects the reflection of the radar signal. So basically this creates issues that invalidates the measurement taken from the VAMOS. This was supposed to be a video of the ACE expedition during the first cruise, which is not working, but you can see it as a picture. And this is how the marginal ice zone in summer appears near the Antarctic shoreline. So we have all this broken ice cover, which is coming basically from the shelf and is pushed towards the open sea by the action of wind and waves. So the VAMOS was the first way that we used to reconstruct wave data in the Southern Ocean, but at the same time, it required the presence of the equipment of the ship. So the question that we had, can we use the ship motion data to reconstruct the sea state even without the VAMOS? So basically, we use the traditional response amplitude operator approach, that's commonly used to calculate the ship motion of the ship. So that's similar to the work that I was doing with OMC, which is the traditional way is to calculate the ship motion starting from the wedge pattern using the RO of the ship. Here we try to do the opposite. So starting from the ship motion of the ship, so we had access to the IMU of the ship, so we knew what was the heave, pitch, roll motion of the ship. We were able to calculate the response vector of this 6 degrees of freedom motion of the ship, and trying to calculate the area of the ship. Our idea was to reconstruct the original wave spectra that the ship was facing into the ocean. So this is as I was mentioning before, this is the standard approach used in the ship hydrodynamics. So we know the sea conditions from a buoy or measurements or whatever. We know the transfer function of the ship, which is function of the properties of the ship, the size, the drawings, and everything. So this is how the ship is responding in heave, yaw, pitch, and the 6 degrees of freedom. And basically matching the sea condition to the transfer function, we transform this data into the ship motion. So we obtain a spectrum of the heave motion or pitch motion or whatever of the ship. So if this is the standard approach, we wanted to go backwards. So we know the ship motion of the ship, we have the IMU. We can calculate the RO. So can we obtain the original sea conditions? So how did we work to calculate this incident wave spectrum? We had the IMU data. The problem was to build a transfer function of the ship. So using NEMO, we tried to reconstruct the academic trenching of RO. The problem is that we had very few information available for this. Drawings were not available, first of all, so it was extremely hard to reconstruct the shape of the hull of the ship. So what we had to do, we were lucky to access drawings from a similar polar class ship, the Gallus. And basically from this drawing, we tried to adapt it to the size of the academic Troshnikov, whatever, the best that we could do. Then we didn't know what was the loading condition. We didn't know what was exact draft, because of course the draft was changing with the loading condition of the ship. We didn't know the GM and other parameters, so we had to estimate different loads and center of gravity of the ship. We had to estimate different submerged parts of the ship. And to do this, what we've done, we've calculated several ROs compared to the different loading conditions to basically make up for all the unknowns that we had in our ship. And then we did a calibration. So what we've done, basically, we calculated the RO using a first guess load, and then using the satellite data of significant wave height, which are publicly accessible to everyone. What we have done, we ran the various load guess until we were getting a good match between the significant wave height obtained calculated from the satellite and the one calculated from the IMU of the ship. So the first guess load was, we noticed these outliers, mainly in the 4 meters significant wave height. Adjusting the loads and the unknowns, basically doing the calibration, we were able to obtain a good agreement between the significant wave height calculated using the two systems. So we obtained R2 close to 0.93. Once the calibration was done, we knew that we have the VAMOS data. So we were lucky that we have a system, another way to calculate the wave height on the ship. So basically, we could compare the significant wave height and the period calculated to the IMU compared to the one obtained to the radar data. And we noticed that we had a good agreement for a significant wave height. Of course, it was not perfect. We have a bit of scattering around especially for the highest value of significant wave height due to the unknowns that still needed to be addressed in our research, and the fact that we were not using the exactly the same drawings of the ship. But we obtained a satisfactory agreement both for significant wave height and for the wave period, the mean wave period of the ship, mainly around between 8 and 9 seconds, which was the most common period faced during the expedition. And then once we've seen that the parameters were good, we had a look at the shape of the spectrum, both for an IMU and the VAMOS, and we found a very good agreement between the two spectra. One recorded from the IMU data, and one basically computed from the radar of the ship. So not only was calculating the HS correctly, but it was guessing also correctly the shape of the spectrum. At the same time, we didn't focus just on the sea state introduction, but thanks to the Antarctic cruise, we had a chance also to observe the wave attenuation in ice on field. So basically, we were able to see how the waves are surviving when they're facing a large ice-covered region of the ocean. So here in these 4 plots, we have the in-state spectrum. So this is the wave spectrum faced by wave, basically before entering the ice-covered region. And here, this is how the spectrum was changing: 5 kilometers, 10 kilometers, and more than 100 kilometers deep into the ice-covered region. And what we noticed is the resilience of the ocean waves compared to what we previously thought. So these are the blue one are the observation. So even 100 kilometers deep into the ice-covered region, we were still getting a much higher peak of the spectrum compared to the one modeling using the Maiden model as was commonly used before. So we noticed basically on field the waves were actually able to penetrate much deeper into the ice-covered region compared to what we thought at the beginning. This is the second and third, if we call it this way, Antarctic cruise in 2017, and the one in 2017 and one in the 2019-2020 season. So the first one was focused mainly on the sea state reconstruction. In the second, in this expedition, we had 3 cruises: the winter cruise, the spring cruise, and the summer cruise. In this cruises, what we've done, we tried to do a different approach, and we focus more using on the cameras on the ship. So using a couple of stereoscopic cameras plus Buoys, we obtained wave measurements, just like in the other cruise, but using a different method. Also, using stereo cameras, we were able to run analysis of flow size distribution, because of course we had pictures of the flow. We could do some statistical analysis of the size and distribution and concentration. Then using Buoys and GPS, evaluated the ice drift throughout the season. And also we were lucky to use the thermal camera, which allowed us to run some sea surface temperature analysis in the ice-covered region to do some to be coupled with the basically thermodynamic of the ocean and the dynamic of the ocean in ice-covered region. So this is the cruise in winter. So if you remember the one that I shown before in summer, you can clearly see the difference of the ice-covered region. In winter, we have a large cover of pancake ice instead of fractured ice. This is due to the fact that winter is forming at the moment, and we have the collision between flows, and this creates this very characteristic shape of the ice in open ocean, which is much different to the shape of the ice and the continuous ice cover more close to the Antarctic continent. Here we have some pictures of how we deployed buoys and trackers onto the ice. So here we have the deployment of the trackers on the Pancake. So basically we were here to track with properties and the position and the drifting of the ice. We have the GPS and the trackers to deploy and track the Pancake until basically the batteries of the tracker were running out or the Pancake was melting into the open ocean. This is the camera setup we place on the Agulhas, the ship that we use for the Antarctic cruise. So cameras were mounted on the upper deck at a distance of around 6 meters between each other. And this is just a close-up of how the cameras were facing the ocean surface. Here is how the stereo imaging works in a nutshell, basically. So we have the two cameras here and here, which are more or less parallel and facing towards the ocean. And the staple of the stereo imaging is that you have two cameras covering more or less the same field of view, but from two different point of view. So basically you are taking a picture of the same portion of the sea surface, but from two different point of views. And this is used to basically reconstruct to the stereoscopic imaging a 3D surface of the sea surface. Here we have just a schematical of how the cameras are connected, and here you can see how basically the field of view is not parallel to the sea surface, but it's actually pointing down towards the sea surface. And here, in this case, the angle was 25 degrees, but it can be adjusted depending where the camera is installed. And here is an example of the field of view captured by one of the two cameras. Here again is a little schematical of how the stereoscopic imaging works. So camera 1 and camera 2 are capturing the same surface but from two very different point of view. So we have the same object but captured from two projectors, basically. Similar, same technology that you have in the three-dimensional TVs. So using two pictures of the same object and doing the cross correlation of the two images, you obtain a 3D version of the object using the stereoscopic overlapping depth of the two images. Another problem that we had to face is the fact that the ship is not fixed, but of course is moving in the 6 degrees of freedom. So, for example, if this is the reference plane, so the one parallel to the sea surface. If the ship in motion, depending if it's rolling, the plane could be like this, could be like this, could be like this if it's pitching, could be like this if it's rolling again. So we had to find a way basically to collapse all the different planes onto a standard reference one. So what we have done using the IMU data of the shape, we were able to reconstruct the specific motion of the ship when the camera took the picture, and basically using post-processing algorithm, we were able to normalize all the picture and move them to the original reference states in order to be compared and kept basically in order to compare similar things and not having any distortion effect due to the motion of the ship. Here is an example of the three-dimensional ocean surface and sea state reconstruction. So this is the image from camera 1 camera 2. So this is the different plane, and this is how the sea state surface is reconstructed. We obtain this basically contour of the sea surface, telling us how the sea surface is moving and what's the individual wave height and everything. And here we can have a direct comparison between the IMU data and basically how the Buoys spectrum is matching with the spectrum calculated using the images. We notice a quite good agreement again between the two datasets, one obtained from the stereoscopic reconstruction and one obtained from the Buoys. And using basically the sea state data reconstructed from the three-dimensional stereoscopic imaging, we've noticed the wave attenuation in the ice-covered region. So starting from the ice-free area here, but basically we had an H max on 9 meters, going deeper into the ice-covered region. So we're talking about 50 kilometers. We noticed a strong attenuation of the wave height the more we were progressing towards the ice-covered region. So the stereo imaging produced data consistent with the findings that we already have about the sea ice attenuation. Not only the stereo imaging is good to calculate the sea state parameters, but it's perfect also to obtain very important statistics about the flow size, dimension, distribution, and concentration. So starting from a camera image, Alberto developed this algorithm which was able to flatten the image. So it's like putting all the flows on the same plane and reducing or getting rid of all the distortion due to the distance and the camera. And he developed basically a imaging detection of the flows, trying to find the edges of the flow and calculate the concentration in a specific portion of the ocean, basically allowing us to see to have a direct idea of what is the ice concentration in a specific portion of the ocean. So this is basically where we are all now and what we have done with all the Antarctic research. Further application that we just started to work on ship resistance in sea ice. As you can see here with ANSYS, we started to have a look at what's the load applied of the Pancake ice-covered region on the hull of the ship. So we want to have a look what's the difference compared to the basically ice-free area, and for the ship stability in this ice-covered region. Ship stability, we started also to have a look also not in the Antarctic area, but in the LNG carrier. So we were starting to have a look of how the sloshing of the liquid inside the ship is affecting the motion of the ship and the critical rolling motion. We developed a CFD model, still an early stage, where it gave us some interesting results about it. So this is everything. A quick recap of the presentation and how according to me, the most important finding of this research is how the ship hydrodynamics and basically 6 degrees of freedom motion of the ship can be used to obtain very valuable data for the Antarctic region, especially because it's the ship motion can give us wave data where we don't have any, and especially in the ice covered region, we obtain some information about the wave attenuation that we didn't know before, both using the IMU data and also the stereoscopic imaging reconstruction. This provided us vital information that we would have not had to run our research. That's it. Thank you for your attention.
Thanks, Filippo. That was excellent, fascinating.
Thank you.
Presentation. Really good to see how you've solved all those various problems with interesting technologies and approaches. If anyone's got any questions, feel free to either drop them in the chat and we can ask them, or if you just want to put your hand up and ask them out loud, that's also fine. Oh, we've got someone joining the presentation. I've missed most of it. If there's no questions, then we're probably done. I think Filippo and Alessandro.
I don't know if Alessandro wants to add something that I missed out on the slides.
No, not necessarily. I think it was quite exhaustive. So.
Very good. Well, your contact details were on the Eventbrite invitation. So if anyone's keen to get in touch with you guys with more questions, then I'm sure that's fine with both of you. Otherwise, thanks everyone for joining in. Maybe Filippo and Alessandro, if you guys just want to hang around till the end, and people can maybe say hi or ask a question if they want, just as we finish up.
Yeah, if I can say something that I missed out from the slides, it's just that the sea-state reconstruction using the IMU data, it's good to obtain parameters about the significant wave height and the main period. Of course, since it's based on the linear theory and the fact that the ship is acting as a low-pass filter, you cannot expect to find all the high tail of the spectrum, so frequencies more than 1.5 to radians per second, but it's perfect to calculate the amplitude of the spectra and the main component of the spectrum.
All right. Okay. Thanks, everyone. I think we're all wrapped up. So enjoy the rest of your day, and thanks again to Alessandro and Filippo for joining us.
Thank you. Thank you for being here.
Thank you very much.
Thank you.
Thank you, gentlemen. Well done.
Thank you.